Thank you. Welcome back to our second part of the knowledge session. It is now the turn of Deborah Amadori. She will deliver her talk about BV solutions to a hydrodynamic model of plotting time. Please.
Thank you, Leonardo. Thank you for the introduction. Thank you very much to the organizers for this kind invitation. It's been really a pleasure to meet in presence with so many colleagues and friends, and also welcome to the online attendees. And the goal of my talk is to present some recent results in collaboration with Cleopatra Christoforou of the University of Cyprus. And we worked on this problem of which is the study of a hydrodynamic model of plotting time. So it is a contribution in this direction. And let me briefly show what is the Thank you very much. So this is the outline of the talk. We will have an introduction on self-organized systems. Then we will present the Euler type model that we are considering and starting in our analysis. The next part will be about the global systems of weakened entropy solutions that we analyze for our model. And then we will consider we address the issue which is interesting for these models of time asymptotic plot. Okay, so let me start with some descriptions of these self-organized systems. What is the goal? The goal is to describe an sample of at this level n individuals that are similar size and similar characteristics, and that have their own motion, which is covered by some rules that tend to make the stable group together. Okay, so we have examples in biology. We see also in this case of Rome that we have this group of birds that fly together, and with the formation of some interesting patterns. So examples of this type are not only birds, but also in insects or fishes and so on. Examples, this is biology, but we have also other examples in social sciences, like formation of opinions and parties, political parties, and so on. Okay, so this is just to give some description, but let's go. What we plan to describe, at least at the discrete level, what we plan to describe is a set of n individuals, which are described by their positions, xi of t is time, and they belong to some region, possibly in dimension, some dimension larger or equal than 1. So this vi is the velocity, and we expect this system of this ensemble of particles to be described as some ODEs. Okay, what is the goal is to describe the long time dynamics of the model, and the long time dynamics is represented that we are in mind to describe is the alignment. So we have a group in which what we plan to investigate is the fact that the relative differences of the velocities of the particles of the individuals as time goes to infinity go to zero. Okay, so they tend to fly with the same speed, vector speed. Also, we have to consider the fact that they stay in a group, so we have this bounded diameter condition, meaning that their relative positions remains uniformly bounded for all times. So this is the type of long-time dynamics that we plan to analyze. Let's go to some models. One of the first models that was introduced and that got a lot of attention is the model by Hooker and Svein that was introduced at the level of particles, and it is described in this way. So we have the positions xi and velocities vi. So we have in the equation for the acceleration v dot I, we represent the fact that the variations, so the acceleration of the particle depends on some average term. So we make the difference of vi with some sort of average of the other velocity. So imagine, for instance, that this k is a constant, then what we have here is exactly the difference between the average velocity with the average of the single particle r. Okay? In this model by Kreismail, this average is weighted by this factor k, depending on the positions of the particles, and this weight function, which is also called communication rate, depends on the distance between the two particles. Typically, it is assumed to be a bounded function, non-increasing in its argument, denoting the fact that particles which are very far communicate less than particles which are very close. So this is the idea. So this function phi that we represent here will be a function which is non-increasing in its argument. Okay, so this was the original model produced by Kreismail, and it got a lot of attention, and it was studied. Sorry. So in the limit of the number of particles going to infinity, it is reasonable to introduce a kinetic descriptions of this type of models, and this is an equation that comes out when we pass the limit of this formula. So we have this kind of equation. We have the transport part of the equation, and we have some non-local term where in this non-local term we have F, which is the kinetic unknown.
Please go on. Okay, I apologize.
Okay, so in this kinetic equation, we have this non-local interaction term, which contains the communication rate k, depending on x and x star. So we have this unknown, which is a function f, depending on x, b, and e, which is a non-negative function. Okay, so this is a kinetic description of the Kreismail model, and passing to further to another level of description, we can have a macroscopic description using then macroscopic variables rho and v. So now rho and v depends on x and t only, and we can get this system in terms of rho v, and rho e. Okay, so at this level, the interacting kernel is described by these non-local steps that we have on this right side in the second and the third equation. But the first equation is the conservation of this. Let me emphasize the fact that when we pass formally to the limit from kinetic to hydrodynamic description, what happens is that these terms P, which stress tensor, and this H plus Q are not closed in the sense that they depend on the F. So when we integrate on in D, so what we get is that we are not able. So these terms here are still including the F in their definitions. And a common way to resolve this problem is to assumption which is called monokinetic assumptions that was also mentioned yesterday in the talk by Simon Gottlieb. And the effect is that these terms are zero. So P pressure term is zero, and Q as well. So hydrodynamic models that are most of hydrodynamic models that are commonly studied are these pressureless systems. Okay. So let me show some references. This approach is nicely described in nicely described in this paper by Singata and Padmore, and further in this paper by Ha and Jean-Beaulieu. And after that, several other models came out and were proposed in order to resolve some problems appearing in the Cooper's-Mail model. And in particular, I'm referring to this paper by Mosh and Padmore, in which it was proposed a variant of the Cooper's-Mail model that was taking into account of a local density of particles. Meaning that if we have a large group of N2 particles and a small group of N1 particles, the small group is not replaced only from the total number, but also from the local number N1. So it takes more into account of the local number of particles and local mass. Okay, so this was a variant that was introduced, and later on this model was included in this paper by this series of papers by Carter and Lewis. And okay, so in this other paper, it was some hydrodynamic model was studied. These papers that I'm mentioning here are review papers. Actually, the second one is a book, a recent book by Roman. Okay, so let me further. Let me continue and let me introduce the kinetic equation that we considered. This was proposed in one of these papers, so by Carter, Lisa in 2015. So they proposed in answer to say kinetic equations, which the variable is still f, depending on x, b, and t. For simplicity, this is the equation. And plus we have some diffusion term here and another term that comes from the Mosh-Padmore equation. Okay, so we have this type of equation, and here we have the non-local term that comes from the Cooper's-Mail. So what they do is to perform the limit for this epsilon small parameter, which represents we send epsilon to 0. So the limit is for strong diffusion and strong alignment. And they perform this hydrodynamic limit and find the equations for the macroscopic variable. Okay, so they end up with an Euler type plotting system in which the variables are macroscopic variable rho, depending on x and p, and e, depending on x and p as well. And differently from other hydrodynamic models, this model has a pressure term. So we see here that there is a P of rho here, which comes naturally from the limit analysis. And in particular, this pressure term is of isothermal type. So this P of rho equal to a constant times the density. So this is a system. This model has a pressure term, so it has some. So it falls within some theory of hyperbolic systems. So what we have here in the right-hand side is a non-local term, which is the density multiplied by the this non-local, so this integral term, which takes into account of the interacting, so the commutation rate k, is k of x prime, density, and the difference of the density. Okay, so we addressed our attention to this model, and what we plan to do is to describe a possibly asymptotic problem. So what is natural to consider? On the initial data, for instance, it is natural to consider that we have compactly supported initial data. So we assume that our density is localized in some portion of space, and we want to see what happens in the evolution of time. And in order to simplify our analysis, we started with the analysis of this system in the case of all-to-all interaction. What do I mean with this? Well, I simply mean that we take k identically equal to 1. Why it is called all-to-all interaction, as the name suggests, it means that even particles which are very far communicate in the same way as particles which are very close. So being far or being close does not matter. They influence each other in the same way. Okay, so we started with this point of view. Then let me replace the k equal to 1 in our system, and we end up with this Cauchy problem. So in this Cauchy problem, I put in this non-local term, I put k equal to 1. And okay, we consider the Cauchy problem for this system. We consider initial data for rho and d. As we said before, we consider the isothermal pressure law. And for initial data, let me be more specific on what we plan to consider. So we have initial data which are contactly supported, and in particular, they are supported in some interval. The interval is denoted by A0, A0. Okay? Outside this interval, the density is 0. What about the velocity? Well, velocity without density does not make much sense, so we set it to be equal to 0 as well. And moreover, let me underline this further assumption. We assume that the density in the support is uniformly positive. So we assume that the infimum of rho 0 on the interval in which we have the support, then we assume it to be positive. Okay, this will be an important assumption for the further analysis. Okay, so let me go on. Okay, so what is our goal? First of all, the goal is to study global in-time existence, and then to study the long-time behavior in terms of asymptotic. So what is our what we expect? We expect that we have time asymptotic clocking if the support, the solution, remains bounded, even if they, of course, they translate. And secondly, that the difference between velocities goes to 0 as t goes to infinity. Okay, this will be, roughly speaking, our definition of time asymptotic clocking. Okay, so let me go on, and then we start with the description of the results of global in-time existence.
The same result is not very close to the first.
Sorry.
So the second one is not very close to the first. Could be that the first is satisfied and the second one is not.
We don't have example. So it may oscillate. We don't know.
Okay.
So the support may remain bounded, it's partially safe, but the V may oscillate in the limit. So this is what we are. Okay. So in principle, they are we have all the two requests, but it's true that in some situations the second one implies the first, and yeah. Okay, so let me state the result that we have. So assume that our initial data are in PV, so bounded variation, and let's assume this star assumption, which is the assumption on the structure that we highlighted before. So we assume that the initial data are partially supported in the interval, and then there is a uniform lower bound, possibly lower bound on the initial depth. Okay, under these conditions, what we have is that the Cauchy problem admits an entropy-weak solution on the half plane T larger or equal to 0. And also we have a structure of the solution, and we can establish that there exist two Lipschitz continuous curves, A of t and B of t, which are the left free boundary and the right free boundary, and a value rho inf positive, where our solution rho will be supported in this interval at every time t. So at every time t, the support of rho is this interval A of t, B of t. And rho is and B is 0 outside this region. And globally, the rho is bounded from below by a positive constant. So there exists a rho in positive such that rho will be bounded from below by this positive constant. Okay, and let me highlight another feature of these solutions. I did not mention this before. We have conservation of mass and momentum for all parts. So let me show with the picture what is the structure of our solution. So we have for P positive, the support of rho and P will be confined within these two boundaries, and the rho will be 0 outside. Okay, let's call capital omega if needed the region in which we have the region in XP of friend in which we have the support. Okay, so let me go on. And let me show what are the ingredients of our proof. First of all, we mentioned before the conservation of mass and moment. Well, where we start from is the fact that assuming that we have a conservation of mass and momentum, we can easily transform our system in a simpler form, which is the following. The system is this in this last part of the slide, and what we have is that we don't see the non-local term anymore, and we see that on the right hand side we have n, which is the total mass, total initial mass, and the difference between v and the average velocity, which is the ratio between the initial momentum and the initial mass. Okay. So what is the idea behind it? Well, first of all, let me show that the right-hand side that we have in our system is, well, it is a rho, which can be carried out, taken out from the integral because it does not depend on x prime. The right-hand side of the system can be written in this way. So we factor out the rho, we have the integral of the momentum and the integral of the mass multiplied by v computed at xt. So assuming that we have conservation of mass and momentum, then we can see that these terms are constant, and then we can easily rewrite the system in this way. So let me comment more. So why do we expect to have conservation of mass and momentum? Well, the conservation of mass is quite natural because the first equation is the standard conservation of mass, so we expect that the integral of rho xt in dx is a constant. What about the conservation of momentum? Well, if we integrate this right-hand side in terms of x, we see that there is a antisymmetric property of this term. So here, assume that we integrate into x. Thanks to this antisymmetric property of this term, where we exchange x and x prime, we concluded that the right-hand side integrating into dx is 0. So integrating in the second equation, we get that the derivative in time of the total momentum is. This happens whenever you have an interacting kernel which is symmetric in its variable, k of x, x prime. Here we have identically equal to 1, so for sure it is. So we focus our attention to this second system, which is simpler than the initial, appears more treatable. And then let's go further, because what we can do is we can translate the average velocity v bar to 0. So we can perform a change of the independent variables x and t in order to have v bar equal to 0. So consequently, the momentum will be constantly equal to 0. This corresponds to change the frame of so the description frame and to follow the group around this center of mass, say. So in the end, we will show that our flock will flock with the velocity 0, but only because we are following the center. Okay, so in other words, the possible time asymptotic flocking of this model will be around a line. So we don't have the mills like we have seen in the fishes examples, but will be around the line with the velocity v bar. Okay. So what our plan is to study global infinite systems, and then what we can use is the theory for and with solutions for this type of systems. And we know that we have global general, when we have a balanced law system in general, we have local existence in PV, and we may have global existence in time in PV under some dissipativeness assumptions that were mentioned yesterday also by the talk by the Fermos. And we refer to these old papers, the Fermos Xiao and the Fermos in particular 95 concerning a similar situation. Unfortunately, the results are very few, as I was mentioning. So there are some, but the theory is not fully completed yet. And in particular, in order to analyze this system, we may assume small data or decaying data as was mentioned yesterday, the Fermos in the talk. Let me also mention that since we started with some system with a non-local source term, we have there are also the results by Colombo and Guerra concerning non-local source terms. However, we cannot apply directly here to global dynamics. So let me go further and what are the main difficulties in the study of these global dynamic systems is, first of all, the loss of strict hyperbolicity due to the fact that we have the vacuum outside the region. So in rho equals 0, we have loss of strict hyperbolicity, so we cannot apply directly the theory of depth. And at this level, let me mention contributions by several authors in different aspects of these models, so the propagation of the compressible flow in the vacuum. And okay, let me mention these results, and I will be more specific later what is in our interpretation of this evolution. And also another difficulty is that we consider large data. So the initial, the assumption, our initial data is that the initial data is a finite total range, positive range. Okay, so let me go on. Okay, the second step in the proof is to pass to the Lagrange formulation of this problem. So we introduce the standards. So we expect the change of variable that brings the spatial variable x into the Lagrangian variable y, and here this is the definition of y. And correspondingly, we pass to the description of the variables in terms of the specific volume Q and P. The resulting system is this 2x2 system in which the right-hand side remains of this type. So we have minus m, which is the total mass, times p. From the point of view of the domain, we pass from a Cauchy problem to a bounded domain problem. In particular, what we expect will be our free boundaries will go into fixed boundaries, and the values for the coordinates of these boundaries are so the difference is m, which is the total mass of the initial data. Okay, so our analysis now is for this system in Lagrange formulation in the bounded domain 0m. Okay. So let us reformulate our problem. So we have the system in Lagrangian coordinates. So this is the region in which study. So y is belonging to 0 and m. And this is the translation of the initial data. So the initial data will be bounded variation of the 0m. The specific volume will be bounded away from 0 and bounded. Both of them are consequence of our assumption on the initial data in Euler variance. And then we are assuming that the average of V0 is 0, which is the counterpart of the fact that the momentum is constantly equal to 0. Okay, so this dy is rho less. Okay. What happens at the boundaries? Well, in the Cauchy problem, we have the free boundary terms. So that's what we expect in our solutions. But when we have a boundary domain, we have to put something as a boundary conditions. What are the natural boundary conditions for this problem? Well, indeed, no boundary condition, basically. So what we impose is this kind of non-reflective boundary conditions, meaning that when there is a wave reaching the boundary, nothing is emitted. So every wave that reaches the boundary just is absorbed by the boundary. So nothing is emitted. Okay, so this is the natural counterpart of the free boundaries in the Cauchy problem. Okay? So about the results on the existence for this system, we have for the Cauchy problem the results by Nishida, 68, and other results that were mentioned also yesterday by Fermos. So, and about the boundary value problem, we have a similar problem, but different in boundary conditions by Amount in this paper, 1996. What about the equivalence of weak solutions between Eulerian variable, Eulerian formulation, and Lagrange formulation? There is this famous long-cited paper by Wagner, 1987, that could be applied to the present framework because it includes also a situation in which density has zero values, so it includes the case of vacuum. Unfortunately, we could not apply it directly because it concerns the case in which the initial data have infinite total mass, so that the Cauchy problem for the Eulerian variable becomes a Cauchy problem of Lagrange. So the results for this paper account for that situation. So we have they account the case of infinite total mass, which is not the case here because we have finite total mass. Okay, so let me go further. So the strategy that we employed is the one away from practical approximations on the Lagrangian system. So we produce piecewise constant approximations, and we employ a fractional step strategy, which corresponds, as it is well known, into dividing the contribution, some sense of the system without the source term. So here we put a 0 in between time steps, Tn minus 1 Tn, so on each of these intervals, and at time steps, taking into account of the source term using this ODE. Okay, so we have these two contributions, so in between time steps, what we call the homogeneous system without source term, and the time step, the ODE in time, including the source term. Okay, what are the strategy of the analysis of our approximate solution? Well, it is common to find some kind of, say, Lyapunov function that are measuring the amount of strength of the waves, meaning the strength of the jumps of our piecewise constant approximation. So there is a natural functional here that helps us, which is the sum of the epsilon j, which are the strengths of the discontinuities, measured in a convenient way. And okay, this is this L in meaning the fronts that are included in the domain. Then we have another function, which is the capital L of t, which is the sum of this L in plus the fronts that have reached the boundary. So the one that reach the boundary stay on the boundary and are there and they stay forever. So what we do is to not lose the information of what reached the boundary before, we park them to the boundaries. So these two functionals are non-increasing in time, and this is a good result because in this type of analysis of a system with the source term, you have actually a competition between what is working for the homogeneous system and what is working for the time step. Usually they don't match. This is why also in case of weak dissipation, you may not be able to control the total variation unless you do some something ad hoc. So this is a lucky situation, and this is due to the fact that we have isothermal pressure. This was also mentioned yesterday in the talk by Dr. Amos, showing that in this case you may even be able to pass the limit in the relaxation. So this is a very lucky case to the fact that we have isothermal pressure. Then we have a uniform bounce on the solutions. Okay, let me go far from that. And then we have this remark that says that this linear functional is not only a mysterious functional in terms of the waves, but it is a quantity that can be expressed in terms of the state variable. Indeed, it is equal to the factor by the total variation of the logarithm of the specific volume. And so this quantity is not increasing in time for this system. And this is not surprising because this is a linear combination of derivative variables. Okay. Unfortunately, this system, so this functional is not enough to capture the more on the structure of the solution. And what we need is more information on the wave cancellation of the interaction. And let me go further. So what we use is an enhanced functional, which is a functional that we call L sub C. C is a weight which is larger or equal than 1, for which we weight more the shocks differently from rarefaction. Here we have negative waves, they are shocks. Positive waves, they are rarefactions. So we give a more weight to shocks. Okay, so we put this weight C, which is larger or equal to 1. And we use this functional was introduced first in a paper with Graziano, for a long time, 2001. Then it was further used in this paper with Andrea Colli, and further in this paper with Paolo Baiti, Andrea Colli, and Santo. And we use this functional, which has good properties. It is bounded, but is not decreasing, unfortunately, in time. So it behaves well at the interaction of waves. So when we have waves on the same time that interact, we have this inequality. So we have that less or equal 0, where here we have not only less or equal 0, but we have less or equal 0 plus this positive term. That where this epsilon vector is the size of the reflected wave to the interaction. So this function has this nice feature, but unfortunately it does not behave well at time steps. So we have to pay this price, and combining the two factors, we are able to control in some sense the situation. Anyway, it helps us improving these vertical traces estimates. So we have that we bound the total variation horizontally and the total variation vertically. In this sense, if we pick up every y in the interval of interest, 0m, we are able to prove that the total variation in these vertical lines are bounded uniformly in time. Okay, and also we have this Lipschitz dependence on the difference on the y value. Unfortunately, this is depending in general. At this level is depending on. So equipped with all these estimates, we can pass to the limit and show that we have a subsequence by compartments. A subsequence converges strongly in L1 log where function UV. That we have this Lipschitz continuous dependence on that we write here. The U is bounded from below uniformly by a constant, and also we have the convergence of horizontal and the vertical traces. In particular, we have the convergence of this vertical trace of V at the bottom. Okay, this will be important in the convergence of the free boundaries when we go back in Eulerian coordinates. And lastly, we find that U and V is an entropy solution of our system. Okay, so our compactness analysis is done for the Eulerian variables, and then the next step is to go back to the Lagrange variable. We do this at the level of approximate solutions, so we define the approximate free boundaries, A of B and A nu of T, B nu of T. So we go back to the original Eulerian variables. We constructed the change of variable that will help us, and we construct our approximate solutions at the level of rho and B. And okay, so this is what nothing surprising, but there is some technical things to do. And we can conclude by the fact that our approximate free boundaries converge uniformly on compact sets to some function. Okay, so this is the result. And as well, rho, the approximate solutions, rho and B converge to the weak-entropic solution of the original. So let me go, nothing surprising at this point. And what we can prove is that we have conservation of maximum. Okay, plain up to now. And now that we have global infinite systems, we want to address the problem of what is the long-time behavior of our solutions. Okay, so let me go to introduce the second result, which is the time asymptotic plotting. So what is? First of all, let's give a precise definition based on the structure of the solutions that we obtained in here and there. So what we will require is the fact that the support of our solution at time t remains bounded, meaning that the supremum over all times of this the length of the interval I of t is bounded, less than infinity. And also we require that the oscillation of the velocity, so the difference between the being two different points of the interval, satisfies the fact that the limit as t equals to 50 is 0. So this will be the two assumptions that we require to define this time asymptotic plot. Let me do a couple of remarks. So the first one is that the first condition, the fact that the support remains bounded, is something automatic, so immediate to say after theorem 1. Why is this? Because since we proved that the overall density is uniformly positive, and we know that the integral of rho is constantly equal to the initial mass m, so we can bound from below this integral, and then we get automatically that the length of the interval, that is the support, the time t of the solution, is bounded by a globally defined, so a uniform. Okay. So the fact that the group stays in a plot is automatic. Let's go to the second assumption that we have to, the second property that we have to check. The second property is the fact that the oscillation of the velocity goes to 0 as t equals to infinity. Let me emphasize that this condition is equivalent to the fact that the difference of B with the average velocity B bar, the one that we defined at the beginning, which is the ratio between momentum and mass, goes to 0. And this means that if time asymptotic plotting occurs, then the solution, the V, will go to the same constant B bar. Here we set B bar equals 0, so we will have to prove that the supremum of B, so that B goes to 0 uniformly in time. Okay, so that the supremum of B goes to 0. Okay. Let me also mention the fact that we have some special solutions. The special solutions are those ones in which the initial data is constant over the interval, and then t is constant. In this case, what is the solution? Well, the natural solution, and those that is also identified by the algorithm in figure 1, is the fact that the solution is not only then the constant solution in density, constant solution in velocity, where the support translates with velocity e bar. Okay, so for this plus of initial data, we have naturally the time sequence. So let's go to the result that we have. Unfortunately, we don't have a general result, but we need to do some assumptions on the initial data. So let rho V be the entropy solution related to some initial data with structure from theorem 1, and assume that a certain quantity, depending on the initial data, related to the total variation of the initial data, is, let's assume that it is positive. Let's give a condition on this bulk quantity Q. The condition is it's ugly to be read, but essentially says that this Q cannot be too large compared with other coefficients of the system. So, okay, what is the conclusion? The conclusion is that our solution admits a time asymptotic plotting, and in particular, we can establish an exponentially fast decay of the oscillation of the rho's. And we can estimate what is the decay rate in time. Let me also say, I did not write it here, but the velocity goes to 0 and the density goes to a constant. So we don't have non-constant profiles in the limit, we have constant profiles in the domain. Okay. There is not much time. Let me just maybe show a couple of pictures, and let me go then straight to the conclusion. So our proof uses two main ingredients. The first one is a functional depending on the generation order of the waves. Let me show it the picture. What are generation order? Generation order is a label that we can attach on each wavefront that counts the number of reflections that we have to reach that front. In particular, let me show, for instance, here. So we start at time equals 0. Our fronts will have generation order 1. Then they interact. There is a reflected wave. The reflected wave will have 2. Then it is reflected again with 3, and then 4, and so on. Okay, in some sense, the idea is that the more you reflect, the more you lose in strength. Okay, so it becomes smaller and smaller. And we need a way to encode this property. So, okay, I will not go further into this, but let me show the other property, the maximum time length. Well, now that we have introduced this generation order, we have a second picture that may help. What is this maximum time length? So we are in a bounded domain, and we have a uniform bounce on the propagating speed, given from below. So in particular, we can establish that there will be a uniform universal time T star, depending on initial data, such that the wave of generation order K exists only up to time K T star. So wave of generation order K either die because of cancellation or die because they reach the boundary. So after time K T1, no one survives. So in this picture, we see that in the first interval, we have generation order larger than 1. The second, we can be more precise and say that we have generation order only larger than 2, and so on. So thanks to this property, we are able to show, I will not go into the detail of this, but we're able to show that okay, we have some exponential decay. In particular, using a new function in which we weight the waves of certain generation ordered by a weight C decay, where C is larger than equal. So this weight increases as K increases. So this is what will lead us to some exponential units. So the time to discuss it. So we have these estimates for B, and overall, let me skip this and go to the result. The result is that we can bound the linear functional L in that we introduced at the beginning with some exponentially decaying function if we have some assumptions on this time, this universal time system. Okay, so my time is almost over. Let me just conclude with a question. So what is, can we say that our system admits, so we say that we are time asymptotic clocking under some conditions. Then we say that we have time asymptotic clocking for every initial data with the structure of this. Well, we don't have an answer, but seeing what happens for the standard Cooper's-Main model for discrete particles, at least, what we can say is that if we have an interacting kernel in which the communication rate, depending on the scalar variables, are, say, it is non-integrable at infinity, so it has a fat tail, in this sense, so it is non-integrable. Then what one can prove is that time asymptotic clocking occurs for every initial data. While if this condition is not met, so there are, you can show some counterexample in which we have that is interacting, so this communication rate is integral at infinity, and you have initial data that may not have time asymptotic clocking. So in our case, we have k equal to 1, so we hope that we are able to reach such a result, and we have some result in this direction. And of course, it would be interesting to extend the analysis to a more general class of interacting kernels. So I think stop here. Sorry for being late, and thank you for the attention.
Other questions from the audience? Please.
Actually, if you go back to the slide number 24, there is this exponential decay formula with the C1 prime. With the next one, the bottom of the slide, there is this C1 prime curve. Yes, as far as I understood, you said that you have some sort of explicit formula for that. You have
Yeah,
something
we can estimate that. Yes.
Okay, and that depends on what?
Well, on the initial data and on this quantity that.
So, but you have some explicit estimate.
Yes, you can relate that. Yes.
Okay.
Because it is related to some choice of the parameters and establish some. It is not optimal, but we have some.
Okay, so it's not optimal.
This is what we can estimate.
Okay. Thanks.
Was there another question from the audience?
Giovanni?
Page 5. Model, just go there, was derived from the one of the previous page, the perception was
Not really, as I remember.
page
So it has a diffusion term. I think it's not directly a consequence of the one in the previous page. It was obtained.
This one, sorry, this one. How was this? I thought this was the.
Yes, this one is obtained in some.
Exception was the two, but it's not the case. No?
Well, it is. You mean from here? This is what they obtained in the paper by Carter Mellet. Yeah, with
So
some.
exception was 0.
So they assume that f epsilon goes to some f, which is represented by density, times the local scale. And they deduce for the density and velocity those equations.
So the
It is a kind of.
model is a kind of leap
Yes.
from
Yes.
this one. I mean, this one over here. It seems they're all, it seems like the terms on the right side are the linear concepts. So whatever
But they show that they disappear in the right hand side. So they take a formal derivation of this, and also I think they prove some kind of convergence as epsilon goes to 0 from mixed solutions to this modified matron. So I would refer to this for So as epsilon goes to 0, they show convergence from the mixed solution of this model to the strong solution. So yeah, as soon as the strong solution exists.
So if there are no more questions, that's all okay. So we thank Deborah again. We have a few minutes for the
Refresh rate sarà 5 Hz.
Are you ready? Ready? Very good. Just the seat. Looks better when you connection to the PowerPoint. I'm sorry. But no, it's okay, right? It is. Yes. It was, you know what this is. It was not known by what I did was to fix this. Because it was not fixed. You scratched it. Okay.
Very good, thank you. We now conclude this morning session, and I'm very happy to introduce Amadori-Klar. I think we all know him from his results, and today he will talk about asymptotic methods for kinetic equations on networks. Please.
So thanks a lot, Ronaldo, and thanks a lot for organizing this conference under all these circumstances. I guess it was a lot of work to get all this under control as well. So my topic is asymptotic methods for kinetic equations on networks, and it's joint work with our Borsche, also from Organizing. This works.
Seems to touch the screen. Ah, yeah.
Oops, oops. So this is the outline. I will start with a short motivation and the ideas of the topic, and then show you something which is in some sense classical. It's kinetic equations and boundary layers of kinetic equations. Discuss this topic a little bit, and then shift to networks and coupling conditions. So it's closely related, just a little bit more complicated problem. So, and then to fix ideas, I will study a specific system. Since as you will see, studying the general case is awfully complicated. It's something you don't really want it. And finally, there will be some wrap up for scalar and linear equations. Your life is much simpler if you can do something more explicit. Nice, it's slow. Take care here. Okay, so the motivation, well, there are classical examples like blood flow in bodies or shallow water flow. At the Fraunhofer Institute in Kaiserslautern, we are more concerned with supply networks like gas pipeline networks, long distance heating networks. That's a very recent topic, just to avoid gas and similar things. And well, this is the practical or industrial problems. For this talk here, I won't talk about these things. It's more fundamental talk. So what is the topic? What we basically do for this kind of networks is we look at one of the nodes of the network, and that will be always the same here. The edges on the network, they will be oriented outwards. Different things, but here in this case, I orient always the edges outwards. So then on each edge you have a kinetic equation or conservation, and we are basically concerned with the coupling conditions. So as you will see for the kinetic problem, it's sort of, I wouldn't say it's the right coupling conditions, but at least the coupling conditions are sort of, well, in some sense clear, if you interpret them in a nice way, which is not the case on the macroscopic level. On the macroscopic level, there's a lot of debates, what is the correct coupling conditions, and many people have done that, and there's no definite answer of this in some sense. And I also don't provide a definite answer, obviously. What I can sort of provide is a kind of, if you accept the coupling condition on the basis level, then I will discuss formally what kind of coupling conditions comes out. That's all I can do. So this is the problem statement now. What you have is a kinetic model in 1D. Let's say first on the line, there's a small parameter, relaxation parameter, and it relaxes to some macroscopic model, which I'll specify later. And of course, you can now transfer all these things into the network. Basically, you define coupling conditions for the kinetic network, and then just let's see what happens if you get the epsilon form equal to 0. What are the coupling conditions for the macroscopic level. And in some sense, you will discuss equations which are sort of similar in more detail for isothermal oil. That's the key thing I want to say. It's not exactly isothermal oil, as you'll see, but some related equation. So what we do, we start with a physically reasonable position here on the kinetic level. As you will see, there will be a very simple thing like particles entering the node, and then by the similar probability going for the other two layers. And well, then the main interest here in this talk is in looking at the detailed structure and detailed situation at the node. What happens at the node? And actually, kinetic layers appear on this node. And they are sort of complicated since they are coupled. The three lanes entering the node, they couple these layers. It's much more complicated than a single boundary value problem. Just that one.
Apologize.
Yeah. Okay. So this is the case here, and then I will try formally to find related coupling conditions. And basically, what we do for this here is to couple the layer to Riemann solve the value of the formula. Okay. So of course the task here is to find sort of to be sure that this coupling even formally is reasonable. That sort of that you find the correct conditions at the situations between the layers, the end of the layer, and the beginning of the macroscopic section. So the starting point for this Riemann problems, which basically means that you make sure that the final state of the layer is sort of an appropriate state for the half Riemann problem at the bottom. It's not clear. So all investigations are, of course, only formal and numericals. Don't expect any proofs. That's something which I would orientate you also do, but that's not my task. And final remark: there is a related work by Hertie, Holle, and Stübenberg, which Yannick Holle did mention already. So in that work, actually, the main difference is that they do that for very special coupling conditions. And using this condition, they basically avoid all the issues I discussed. So that's the difference. But of course, we have much more results. That's the other one. I have just formal results for one of them. So that's the. So as I said, we will first discuss a simple lane, a boundary on the left of the lane, and then look at the kinetic problem in this lane or in this edge, and let's see what happens if the limit as the assignment goes to 0. As I said, this theory is classical, and that's the second graph. So you have here your kinetic equation for a distribution function in space and in velocity. You have this standard form. I don't specify the collision operator. That's not really important. It's important for calculations later on, but not really important at that stage. Then you have some macroscopic quantities, let's say the density, mean velocity, and probably further quantities. And what then an asymptotic analysis gives you for epsilon going to 0, gives you macroscopic equations for these macroscopic quantities. That's well known, of course, for lots of problems, in particular for the Euler equations or full Wolfram problem. You might get here, depending on the collision operator, you might get all kinds of limit equations, linear, nonlinear, scalar, or systems. That's in some sense, kinetic does everything. So that's the situation on the lane without boundaries. So if we add now the boundaries, then first thing you have to observe is that for these kind of equations, we have to prescribe only the ingoing characteristics. That's however very simple in some sense here, since it's just a positive velocity. You prescribe a distribution function on the positive velocity. And you don't know the ordinary velocities, the negative ones, of course, that's something which you have to compute. And if you do now this, the limit epsilon to 0, you observe that at the boundary a layer, so-called kinetic layer. And well, let's discuss now first of all this layer. This has also been done. And what people did here at that point is something which you would also do for any single ODE. Just do an expansion. And what you usually do is you have asymptotic expansion, and basically here's some order of epsilon, which I did, right? But there is a leading term here, That's a so-called layer equation. And you get the equation for this leading term by zooming, so by scaling the space coordinate layer with this ordinate designer. It essentially zooms the situation inside the layer to a half space from 0 to infinity. So this is very classical, and then finally, well, finally you get the solution of the layer and the infinite value of the layer. This has to be matched to the macroscopic equation. Of course, it's a bit tricky now since there's this hyperbolic problem there, and we know that you cannot describe everything. So there's the Riemann problem and the half-Riemann problem there. And that means the macroscopic solution here has to fit for the admissible states for the half-Riemann problem. Otherwise, you have no match, not even on the formula. So this is this one, but still looking at the layer. What you can easily see now, doing the scaling, going to the first order epsilon, you end up with such a half-space problem. And this half-space problem, well, you just take the left ingoing distribution here at 0, you take it to be the thing you have, that's your distribution, and then you try to solve this half-space. So now a few remarks without going into too much detail here. Well, for a unique solution of this half-space problem, actually we need some partial information at infinity. So you won't be able to solve the problem just by knowing the ingoing distribution. And that's in some sense natural, since that's the outgoing information from the macroscopic equation, which provides you with this ingoing information from the half-space. So there must be sort of a relation between that. So the half-space problem needs conditions at 0 and at infinity. At 0, it's the thing you have here, but at infinity, it's the outgoing information from the microscope which provides you this condition. Then you solve the problem, and then you get the full state at infinity, at L infinity, and that gives you then the state for the Riemann problem, for the half-Riemann microscope. So that's the idea behind these half-space problems. And well, that's the thing I just mentioned here. So that's this matching procedure. And now let's look at these half-space problems. Of course, this has been done in theory. It's a topic which has been discussed for, I would say, since 20 or 30 years. It's still ongoing. People did a lot of work on in the linear case. So there are many analytical numerical results, approximate solutions. So it's François Bolzmann, one of the driving forces around 2000. That. But I didn't really conclude that here. It's a tremendous list of people working on these problems. And for the linear case, also I would say the situation is more or less it's pretty clear what to do. And that means we can also use that nicely in the linear case for doing this coupling. Everything works. But if you are in a non-linear case, there's a huge problem. On the one hand, you cannot linearize, since you don't even know around which state you want to linearize. There are these 3 lanes here. So is it this state, or the state on the 3rd lane around which you linearize? So there's no way to do this linearization problem. You have to look at the non-linear problems. And then you start to read the literature. And then the big messes appear somehow. Since the non-linear kinetic problem, there's a nice survey paper by Claude Bardos and others. He's describing the half-space problem. And it's really that's a really messy thing to do. It's not really, there's no result, even not the existence result, nor more qualitative result. So they're still pretty open. There are some weekly non-linear results, but not much more. And then there are some even quite complicated results using the matching procedure by some people, which use very simple discrete velocity. If you want to prove, then you might look into this paper, for example, by Lico and Sin, and it's a tough paper for the column. It's really nothing for 3 velocity knowledge.
Ends up for verified gas dynamics, or
I think this is verified gas dynamics. This is just the column ones. This is 3 velocity. So it's no real application. Okay. Cool. Yeah, you did right. This is correct. It's very cool. Okay. But at that stage, somehow one has the feeling, I will give you some more literature later, that it's probably a good idea to change to discrete velocity balls and not stick to the full balls control. That will be something you will not be able to do. So the project is doomed if you start to do it. Okay, so we did that, but now, oops. It stops. So I shortly described now the network formulation. So what's the principle for the network? So for the coupling conditions now, what we basically did is on the kinetic level, we have to prescribe all ingoing functions e bigger than 0. Remember the orientation was out of the group, so we just have to prescribe the positive velocities for all ingoing functions ijk. That's my numbering of the different sections, and then we assumed here a linear combination of the output. And in the simplest case, so there's now a matrix of distributing these things left and right, wherever you want to go. And in the simplest case, you just use a half-half distribution, which basically means you have now a particle starting here, so there's a flow going into the node from that side, and then there's a probability 1/2 that the particle moves to the left and right. So that's the physical interpretation of this condition here with this, let's say, this. And that's true for all other nodes. Particles coming from here, they are distributed in 1/2 each of the other two nodes. So, and in most considerations, we restrict to this completely symmetric case, since it allows somehow to exclude some combinations with the symmetry. But it's in principle not necessary. You could also use different conditions here, like more dissipative conditions, like but this is the simplest thing. Okay, so that's the kinetic condition. Again, there's one thing you have to take care. You have to take care to guarantee the conservation of mass. Otherwise, it's not. Your load would somehow take off particles which you don't like. But that's easily done. It's just in this matrix C. You have basically to make sure that the rows or columns that they add up to 1. That's all. So this is the restriction of these conditions. Okay. Then next step. Oops. So this is the problem now seen in view from the epsilon to 0 situation. What we have now is you have the kinetic problem here on all these states. You have this connection at the node via these conditions I've just shown you. And what you have to do now basically is you have to, on each of these lanes, you have to do the boundary layer analysis, which I explained before. So essentially that gives you for the ingoing values or functions of the layer problem, that gives you the same conditions again. So that's the way how the ingoing layer problems are connected. The ingoing distributions of the layer problem are connected at that point. However, remember, all these layers, they require conditions at infinity to be solved. So what you have here is now a bit awfully coupled problem. It's coupled here, and via the condition at infinity, it's also coupled to the solution of the microscopic equation. There's this coupling here now, which goes, if you prescribe now something here, some mission data here, then this will affect the solution in all other roads. So that's the situation, and basically that's the same picture now. The figure is like that, but I just explained the second ago. You have the node here, you have the layer first, then you have the value at infinity of the layer. You have to match this value at infinity of the layer to a half Riemann microscopic solution. Just imagine this is now the isothermal Euler solution. So this is the situation, and then you have sort of a couple of that will give you the limit. So as I said already, I don't want to do that for the Approximate problem, and it took us some while to find a nice model problem. To be honest, In some sense, you have to find the body problem, such that it's simple enough, but also that it's rich enough to have a nice layer. If you just choose a very simple one, you don't have a rich enough layer coupled to that. And actually, the thing we finally came up with is it's actually a sequence of models which have been used by nuclear salt, by heavy. It's so-called discrete. It's a discrete velocity K model. So Ludwig used that for solving the Boltzmann equation. And what I'm doing here now, for this example, is just take the first one of the hierarchy. And now let's check the find. So, well, the model goes as follows. It's just 4 velocities. So that seems to be enough to get something like an isothermal Euler with 2 quantities. So we just need a bit, of course, more. But 3 is not enough for now. With 3, we won't manage to do it. But with 4, it's fine. And what you do then, it's already written in the form of a classical BGK model, but on a discrete level. The I is just going from 1 to 4. We have 4 velocities. They are symmetrically distributed, -1, -W, W1. And of course, now the ingoing quantities are those, the positive velocities are just the 3 and the 4 velocities. They enter at 0. These are the positive velocities, and the outgoing ones are -1 and -W. And of course, W is chosen between 0 and 1. As you will see later on, all quantities depend on this W. So then you can obviously define now the moments. And there's density is just summation, there's infinite flux, there's the second moment and the third moment. And you don't need more. Since you have only 4 velocities, you should be able to find a system which is equivalent to that one. Just that would be the associated moment system. So what you do then, and that's Glück's contribution in that case, you choose, well, the max radians, MI here, you choose them in such a way, actually in this form, like an exponential with some coefficients A and B, such that here the summation over the MI is density, and the summation over VI MI is the flux. So with this choice, you simply guarantee that these are collision invariants, and you guarantee that mass and momentum is conserved by equation. And you have additionally, by doing that, using the exponential here, you have a sort of couple of very nice conditions. You can prove a lot of things for these problems then automatically with entropies and all. It's very near to the Boltzmann equation to the BGK equation in this discrete setting. Well, so that's the model problem. And then let's look at the nonlinear, at the moment system here for that. And first of all, note that the velocity Q over rho, that this is now bounded between -1 and 1. And that's obvious, since the maximum velocity V was 1. So I cannot generate anything which has velocities above 1. And that will affect, of course, the macroscopic equation, the resulting macroscopic equation. It will not be like the Euler problem on R, but it will have velocities between -1 and 1. But let's go back to you can close the equations now just by a simple computation. And this is actually the resulting moment problem we find. So this problem here is still equivalent to the kinetic problem. So you have here, you see the conservation of the continuity equation and the conservation of the first momentum as well, the momentum flux here. And then for the other moments, of course, you have some relaxations. Relaxation is now concentrated here in 2 quantities F and G, which have to be computed. So and now you can already check what the macroscopic equation is. It's very simple here at that stage. We just let the epsilon go to 0, then the epsilon is equal to rho times F of Q. TE is equal to rho times F of Q. Then you plug it in, and you have your macroscopic equation. That's it. Always remembering that velocity is Q over rho. And well, obviously one doesn't need this G for the macroscopic thing, but one very well needs it for the measure, for the kinetic layer. It's not needed on the macroscopic level, but it basically describes the effects of the kinetic. So that's this one. And that's the macroscopic equation. So it's the equation here we have just discussed for epsilon to 0. And the good thing here is actually the system is rich enough. It's in fact a system which is around, is sort of equivalent to systems which you obtain by a maximum entropy. And you have a lot of properties which are similar to isothermal Euler. In particular, you have the following. You have eigenvalues with identical sign if the flow is supersonic and positive, so between some u tilde, which is the sonic speed, and 1. And with the absolute values between them. And they have different signs if the flow is subsonic. If it's just between, if the absolute value is smaller than 2 tilde. So that's similar to the Euler case, but of course the U is restricted to -1. And the U tilde plays the role of the sonic speed in Euler. It's the same thing. So here this, well, this has been actually, there's a couple of papers you can look at. A paper by Mobilev and Lausdorff and Barthelin, Saras and Bushina, I think. They are not really looking at these kind of models, but you can use several of their ideas to transfer this case here. And this is the reference to it we saw in general. We did not look at layers, but at the problem in general. So this is the situation, and now let's go on. Well, the half-space problem now, that's nice in some sense. Since, of course, the half-space problem, you get the half-space problem just by letting the dt, by erasing the dt. And that's now this problem here. And obviously, if you look at this situation here, then if you kill that one for the half-space problem, it's just Q is constant, E is constant inside the layer. And that's a very characteristic thing for analytic layers. Flux is always constant, and then potentially also higher moments, like here the second moment. And all what you're left with is this system here, the remaining system, and that's what I've written down. So the remaining system, that's now just the dynamic system. Two parameters. And I mean, unfortunately, there are two C and E are coefficients. Of course, we are not allowed to fix them at the time being. They will be fixed by the macroscopic quantities. But it's a dynamical system now, with well, depending on two parameters. So now you have to investigate that, and then there's a nice observation, which actually has been done already by Bobby paper for this case. Now, to check that, first of all, of course, always you check the values of infinity and fixed points of the system. You observe that basically the ratio D over C is the important thing. And you observe then that there is a certain ratio D over C, then you get 1 or 2 fixed points. So here, and this fixed point depends just on the ratio. And you get more. You can basically, it's not completely explicit, but essentially explicitly. And you get more. You get, if there is only one fixed point, then this fixed point is in the subsolid region. And then this fixed point is a center. If, in case there is a second fixed point, then there's still one fixed point is a saddle, but the other fixed point is a sink. As long as we are in the region where the fixed point is supersonic but negative. And it's an unstable fixed point if we have a supersonic situation with a positive velocity. So these are the three things which can appear here, and that somehow fits perfectly well to a sort of a simple consideration of the characteristics of the macroscopic problem. So in some sense, if the fixed point is unstable, it's the supersonic positive case, then the layer is nothing. The layer is just a constant. There's no choice, no other choice. The layer can't do anything. There's no way, it's just a constant solution. Then the macroscopic problem has to do the job in this case, in the supersonic positive case. But in this case, the macroscopic problem also sort of, as you can use the 1 and 2 base in the real problem as it is found. In the case that you have a supersonic negative, in this case, well, the fixed point is a thing. So there's a domain of attraction around the fixed point. And you can attract a lot of starting values at 0 to your fixed point. And then the macroscopic problem doesn't have to do a lot. Almost nothing. In this case, if you look at the characteristics, it also cannot do a lot. There are two negative characteristics. This is the simple cases, no positive characteristics. So that fits, and in the case in between, it's a cell. So there is a stable line in the cell. The stable line is fine on this line. On this line, you can transport the right value of 0 to the fixed point. But not from the other directions, only on the stable line. But the other directions, we are taking care of two waves in the macroscope. That's the sort of how this is combined. And this is, it gives you a certain confidence that the method this should work. It can be nice to see here. And now it's a, well, that's a, you have now to look at more carefully at the centers and the fixed points, so on of the dynamical system. And that's basically, but we changed a little bit the description, but here it's always u in my description now, it's velocity. So that goes here from some value to 1, and it might also go to the negative side later. But here it's only positive values of u, and you observe now that depending on this ratio, you get different situations. You have actually bifurcations now. The problem bifurcates, it goes from no fixed point to 1 fixed point to 2 fixed point, and again to 1 fixed. And this bifurcation here is exactly in this situation, there's only 1 fixed point, well, it's numeric. In this case, you have a stable line. The stable line is always blue. Forget about the red lines, they are unstable lines. So you have a half stable line only for one side, in this case, and that's the situation with the sonic fixed. It's a sonic point. And in case of the sonic points, you have still in the dynamical system such a stable line. And now you can choose here on that point, that situation here, you can choose now a value on the left-hand side, and it will be transported to the fixed point, and from the fixed point, actually the sonic reflection wave transports to the situation. That's situation 1. This is a situation with 2 fixed points, an unstable fixed point here, in this case, stable fixed point, and again you have such a stable line going from the unstable supersonic to the subsonic point. And you have a situation where you have only 1 fixed point here and no supersonic fixed point. In this case, you have only the stable line to transport you to the fixed point. So that's the subsonic situation. This is kind of the supersonic situation with an unstable fixed point, and that's the sonic situation. And similarly now, so this analysis goes on. In the negative case, well, in the negative case, it's even a bit more complicated. You have a sonic situation, sonic point, with a domain of attraction around this sonic point. So you can use now any point here in this region on the left part, on the left boundary of your problem. It will be transported to the fixed point, and then the macroscopic solution, the Riemann problem solution. And then there are other situations like the situation with 2 fixed points, where you have again the domain of attraction. So this is a bit bad from the point of view of plots. But the domain of attraction is just the region between these two plots, and here it's also the region between the two. And then you have the case with only 1 fixed point, it's just subsonic. So this is the situation here. And of course, we are not allowed only, we have to discuss now also the hyperbolic problem, not only the kinetic, the dynamical system. But the hyperbolic problem, well, let's look first at the Riemann invariance. That's easily done. We just use the Riemann invariance here. So it's the one curve looking like that. It's a bit a strange way of I'm looking at that in cube. So this is velocity. This region here is the supersonic region. That's the supersonic negative region, and all in between is the subsonic region. And this is one final point. And these are the 2 curves, which are more important for us, of course. So the 2 curves are the curves in the subsonic region with the positive velocities. They can be used for prediction. Let us know. As we look at our figure. So it's similarly for shortcuts. And having done that, well, all you have to do now is you have to read the Lieber Schrock paper, write down Lieber Schrock picture. I did that here in one situation. So it will basically give you now, if you have a predefined macroscopic data on the left. I've chosen here supersonic macroscopic data. It gives you all states which can be connected from the left to this state. And all these states, they are given here by this picture. It's here the two curve, the positive two curve until that point. And it's all states inside of this blue, like a rectangle. It's not a rectangle. All states. So essentially, to solve the coupling problem now, what you can do is you can choose all fixed points from this Lagrange domain, and then you have to make sure that the stable lines in the asymptotic domains of attraction connect. So here it's pretty obvious what you can here in this blue region. You connect all of them by one or two curves. Here in the subsonic region, you have just the two curves to connect, but you have a big choice of different fixed points. And then there's one more fixed point here, which I don't not specify. This fixed point is a sonic negative. And this fixed point here is a single point, but here you have the domain of attraction. And doing that, I didn't really think that it would go well. So the task is now on the single lane. You have to find now for each of the possible fixed points, which can be connected to one of the macroscopic data by this blue on the flock picture. You have to find the ingoing data on the stable curve or in the domain of attraction, and that will give you this combination of this matching. So from here, from the left part of the layer to the infinity, that's either by the stable curve or by the domain of attraction of the fixed point that transports you to that place, and then the half-Riemann problem takes over from the V1 from. So this is the situation. And the funny thing is that really works in this case. So it's surprising. So at least me, I was surprised that it works. So it's you can even completely classify the domain of ingoing kinetic boundaries. So of ingoing kinetic values. So this is the plane F3, F4. These are the ingoing distributions, the positive distribution values. And then the classification is as follows. You can connect now any point here. I choose a point, for example, in this domain, the blue domain. This means I have to use unstable fixed point here. That means the layer doesn't do anything, the layer, but here the one of the two waves in the connection. Down here, I have just subsonic fixed points. Here, I can choose the fixed point on the two curves on the fourth picture, and additionally, I have the stable line to connect everything. Up there, that's a big region. It's a surprisingly big region. It's just a solid fixed point. And well, why there is such a big region in the sonic fixed point case, positive sonic fixed point case, is there's only one stable line here. But if you go back to the V1 flock picture, there are actually many solid fixed points. So there are the solid fixed points on all this line here, which can be used for the connection. And then you go from that and use the stable line of the solid fixed points. So then there's a final thing which you don't see in the picture. There's a very small dot here. And this dot here is actually, that's a zoom into this dot. That's actually all the states here inside of this triangle-like thing, which can be connected by solid negative fixed points and by the domain of reflection. So that's basically in the V1 flock picture. It's just using this this point here, only this point, and solid negative. But that then covers everything, and you get here. I mean, it's completely formal. It's no proof, of course, but it covers the whole domain of possible ingoing values. It gives you sort of numerically. You can now just pick out one of these things, and you get the numerical result. So typically here you see, I mean, these are just two solutions. Here's a subsonic and a sonic fixed point. You start now with a certain initial datum, and you get here, it's always supersonic macroscopic data, but you get here subsonic data. So it's just jumping over the sonic line. And similarly, you can get out of here in this case, it's positive case as well, supersonic macroscopic data in the beginning, and then you have a kinetic condition here. you get this thing here now is well, here the same. This is the kinetic layer, and this is actually a two-wave. So in this case, this here is the kinetic layer up to this point, and at the solid point, a two-wave or rarefaction wave takes over. Then you have here in this region here two rarefaction and one shock wave. You can use the one wave here since you are supersonic. So this is exactly actually what the result of this numerical comparison, but the results you have computed from these considerations fit exactly to the numerical computation. So that seems to be sound. Well, now I have probably too much. So this is now very shortly, just to tell you what I mean. As I said already, we need now a coupling of all these things. That gives us a couple of conditions. You can figure out that you have a balance of certain momenta of the flux, of course, but also of the third moment, always in the moments which are not the uneven moments, and you get a couple of invariants. And these invariants altogether, this gives you just 6 equations now for 12 quantities in your kinetic problem. This correction. And what you have to do now, and that's the nasty part, you have to distinguish now between all these cases. And then the fixed point, each of these 3 fixed points is unstable, is solid, or is, sorry, in this case, or is in the asymptotically stable. So whether it's supersonic positive, whether it's solid, or it's supersonic negative. So you have these 3 options. In this case, you always get related conditions. You can use these conditions, plug them in, and then you get equations for all these situations. I don't think there's any way around it. So you have to discuss actually 8 combinations. You have to discuss combinations of 2 supersonic negative fixed points, 1 supersonic positive fixed point, and of these situations. This has to be solved, and I just showed you the numerical results. That's a typical situation here. It's actually quite funny. So you have an inflow here on this part of the network. You have 2 outflows here on that part. And what you observe then is a general increase in flux that's consistent in other conditions. And you get a small, so this is the node here at that side. You see here a small layer, that's the domain of attraction. Then you have a reflection wave that connects to the microscopic picture. And on the other side, you have a bit of a bigger kinetic layer, and you have again a 2 waves going out. So this is the way how this generates now these conditions. And of course, now you have the coupling conditions. The coupling conditions basically are fixed points, rather than fixed points. These are the microscopic coupling conditions. Unfortunately, it's not very explicit now. It's very implicit given by the solution of these equations. So this is the situation. Here, I just want to mention one thing. Let's say if you look at the 2 solid cases, it's somehow instructive to look at the linearization. In this case, you can do some explicit calculations, and you observe a certain coupling invariant. That probably answers at least some of the questions you might have on the conditions for the Euler condition. So there is a certain coupling condition. But as you easily observe, this coupling invariant is neither the equality of the momentum flux, nor the equality of the density. Nothing else. It's the equality at the nodes of a linear combination of the flux and of the momentum flux, which is the expression for C. And the exact detail here of the coefficient, this is the kinetic ingredient. This is all what kinetic theory gives you here. Is the value of this coefficient. If you start with different kinetic problems, then you will end up with different coefficients. And that gives you different solutions, of course, different invariants problems. So this is basically something we take out of this analysis if you do the linearization. Then it's a pretty closed form. Then we know now the invariant which really fits to the kinetic form. And that was basically the discussion was always, is invariance of the momentum flux correct, or is invariance of the density correct? And this is now just a sort of combination of this. So just correct. And now probably I just do that by words, not in detail. I didn't tell you now about this linear case, and in the case of a scalar limit equations, you can be much more specific. In the linear case, the whole thing boils down to some matrix analysis actually. You can now evaluate the matrices, you get nice conditions for this case. And in the case you have only a scalar limit equation, it's sufficient to take the two velocity system. In that case, you can get explicit coupling conditions. Just use the supply and demand analysis. You can write them down explicitly. Actually, we did hope for something like that here, but that doesn't seem to be possible in this case. So now let's just jump. We'll ask some investigations on that. I'll just skip now. But in this case, you can now probably investigate that. But this is the conclusion now. So we have done this formal investigation in the non-linear case. And just remember that in the linear cases, this is much more explicit, more determined. I want to do one remark about the numerical side of the problem. So you have the feeling that it's not a good idea to do that numerically to solve these complicated non-linear equations there. Of course, you can just as well solve the kinetic problem using scheme. But then be aware that to get a reasonable solution, you must resolve the kinetic table, which means you have to use a grid step size that is possible order of this. That's the price you have to pay. And finally, well, what should be done, of course, is to extend that to nonlinear models with more condition invariants, leading to kind of full order equations. In the linear case, we have done that in those similarly. And of course, I don't say anything about that. Theoretically, it's basically I don't think there's any reason for this, even not on the board. Okay, thank you.
Next slide. Are there questions? The audience, please go ahead.
Thank you, sir, for this nice book. And it's a very interesting program.
I would say it's more a program than a solution to be honest.
You're right.
More questions than answers.
Exactly. I mean, think of this in terms, say, of traffic.
Yeah.
Which in a sense would be simpler because you'd expect the signal what is going this. But then you would expect, say, that the matrix that we distribute and the node will not be constant in general every step, right? So for instance, we have a node for this club, the node will be over there. So this is one thing. Another thing that is more a curiosity is you're using this single velocity W.
Yes.
And that means to four velocities to be on. But you end up with having this third moment of order 3, which is unusual even compared to why does W not work?
If you use a W, okay, let's answer the two very good questions we actually investigated. So I'm done with that. So W going to 0, that's actually, it looks like as if this would be a simple choice. But then you end up then with a three velocity problem. -1, 0, 1.
Yeah.
In this case, the layer is not rich enough to do it. It doesn't work. We won't be able to do the connection fast. They actually do this paper by Liu and Sim. They are actually discussing such a thing. You have to look at moving layers and so on. It's much more strange. It doesn't fit to this. It's not enough. There is a macroscopic solution, of course, to prove that, similar to that one, but the layer is not sufficient to have this structure of supersonic and subsonic disk points, which have to fit to the visualization. Which doesn't work in this case. We could use, of course, more velocities. That would still work. That's even more crazy. So then the question, second question, since that's also a very good question, it's about the traffic flow. In the traffic flow case, we had some trouble, to be honest. And the trouble is more fundamental. The trouble is you cannot simply start with a simple two velocity. What you have to do in order to do something really physical, you have to find a model which is essentially a model which preserves positivity of the gates, which the two-velocity model doesn't do. Remember, the two-velocity model in general is just a wave equation. It generates out of positive data, it generates intermediate states in the river from which are negative. That's not suitable to describe a traffic flow. We need to have positive ones. And then you have a trouble. Since it's not, we won't find a linear main path. Such a model with a linear main path, so you have to go back to non-linear ones. Let's say, for example, your raster model would be your raster model with relaxation, would be a typical model where this works. But then you have to discuss instead of the linear parts, linear models like dt, f plus v plus f, you have to discuss non-linear models. And then even the boundary layer analysis looks much more complicated. It's a funny picture what you have to do in the boundary layer analysis. There are zero shock waves and all these things simply to connect the boundary layers properly. So non-linear case, if you use the non-linear case instead of kinetic problems, you just shift the problems. So that's the second thing. So what you should do, what I should do is you should look at the raster problem and try to do this analysis for the raster problem and the convergence to the likelihood. That would be the problem. Then I said it's already for the boundary layer analysis. It's not straightforward. So the coupling is a lot of cases. Problem. Numerically, of course, that works. That's basically the answer to that. So it's the positivity problem which kills you. The positivity of this. It even kills you formally. It doesn't kill you, but it creates other problems.
I had the question, but the one was already answered. So I want one question, which is basically in principle you can solve this boundary layer problem if you are in the case of the scalar equation, you get only a single function because you have only one.
I didn't show it anymore. It was a bit, but that's a scalar problem if you just have two velocities.
So basically, what happens is you have to find that the relation depending zero,
Exactly.
which is why the single function, which is technically
Yeah,
a table of that, right?
if you take a look up, when this is very in the case of the Burgers problem, that's very simple. It's just the square root of the flux. The flux is u squared, and the thing you connect to is the square root of it. It's u. If you have u plus dx u squared.
But even in the case of four velocities, we have a function which is a function of two variables. They also invincible for many values.
Exactly. Of course, you could do that. You could take it up there and use that numerically. Right. Absolutely. And that would be, I think, numerically the only option I do. Everything else is much more. It's like a table lookup. That's very reminiscent of things that Yoshio Sone and his group did on this for the boundary value problem. They actually did numerically huge table lookups for the nonlinear problem. That's not for the couple problem, but for the boundary value. But just as a remark, here you also observe the unstable layer and the asymptotically stable layer. And if C goes now to infinity, it's just one line here. You have a half stable layer. So that's the same as the stabilized I showed you before in the 2D.
Thank you for the question. I have a short comment. The fact that all these procedures were made formal means there's a lot of job to do. So I'm referring to all the young people in the audience. Okay, you have a lot of things now. Then you also have maybe two technical issues. You know, there is this paper by the son that says that the end up order at a junction usually gives you solutions that are where the total region can blow up. So do you expect to find
Actually, we discussed that and we thought maybe there could be some sort of solution for that, but I don't want to say too much in this respect, to be honest. I don't really feel comfortable with doing here any I really don't know whether this helps. It's on this level here, it's purely formal, but it's sort of I mean, this observation that it works, this classification observation, it's a nice observation. So it gives you some confidence that there could be probably more, but not more. I know this problem that it's we saw it in the video. I always said to solve this problem. So, but nothing else.
Yeah, yeah, very good.
We'll see.
So we all thank the speaker again.